Hi everyone. Well, it's a new day and another problem. Because I am an instructor in astrophotography videos, people will send me through, especially the forum at atomblockstudios.com, they'll send me questions about things. And like Sherlock Holmes, there would be a crime, but not necessarily the most spectacular crime. What mattered is if it had points of interest. And this problem I have today, I think, has a couple of points of interest, so I want to show it. It's not that, this is a very common problem. It's not that there is something difficult about what's going on here. But as I say, there are a couple of finer points of interest that I think really make this for a compelling video, just to point out some of these things. All very useful in an understanding of what to look out for when doing astrophotography. So, the way the problem was presented to me is that there were a set of images that this particular gentleman took, and he found that the satellite trails were not getting completely rejected. So what I received in my forum was an image that looked like this, and what it shows is, through the field, he's got a very nice data, which I'll show you in a moment, of wide field data of the Whirlpool galaxy, which is in the bottom right corner here. But if you zoom in, you can faintly see, sure enough, there are satellite trails that are just not entirely, completely rejected here, and you can just see them dimly, faintly running through the field. What he presented this problem as is that he has actually two sets of data. He had a set of data that was 45 seconds, another set of data that was 2 minutes long, and he described how when he combined the data, he did all of these experiments. When he combined the data that included, when he included the 2-minute data, he always had the remnants of the satellite trails. If he didn't include it, well, he could either not see them or they would somewhat disappear. And so he needed to understand what was going on. He thought the problem was with the 2-minute data. Kind of the answer is yes. So one of the things, of course, to recognize is that when you combine a whole bunch of data using image integration here in PixInsight, fundamentally, you're just averaging images. So the more images that you put together, the fainter some artifact is that's only going to be in a subset of images will appear in the final result. It still may be visible, just like these satellite trails are visible here. So my logic was, well, sure, the 2-minute exposures are kind of the problem because they must have the satellite trails. So I asked him to just give me the 2-minute exposures. I don't care about the 45-minute exposures. Apparently, they don't have any significant satellite trails in them. And this is what his data looks like. Here we have, I'm going to move this out of the way, wide field imagery of M51. And if we flip through the frames, indeed you can see running through frames satellite trails. Nothing uncommon these days. In fact, here is one of those trails that we see a remnant of, and probably here is another one because I can see how they're crossed in the example combined image that he showed, and so on. I also want to note on a completely different topic that if you look here at his output, this output is coming from a normalized scale gradient. So the output that he has here, that he's given me, are the 2-minute exposures that are normalized through NSG, this script. And so this is very good stuff. He has an excellent starting point here, and it should lead for excellent rejection. So this is one of the finer points. This is the point of interest. Why, if he ran this through normalized scale gradient, why aren't we getting excellent rejection? So that was a thing that compelled me to want to take this up to see what was going on. Look in the list here of blink. One of the things that normalized scale gradient does is it outputs the weights that it calculated per frame in the file name. So you can see that the reference file, the one that has a weight of 100, is the first one here in the list. And you'll notice that there are a lot of other frames here, but they're not nearly as good. They have different weights. And then there are a couple down here at the bottom that are quite similar. So I just want to mention that if we kind of move over here to the galaxy, we can see that if I flip between two of these frames, you can certainly see that one of these frames is much dimmer and noisier than the other. So normalized scale gradient is certainly doing its job. I can see that with my eye and my brain. But the reason I want to point this out is that if and when you load this into image integration, normalized scale gradients can turn on and off some threshold weight that you specify. It doesn't have a meaning. It's only for useful purposes to tell you, hey, these data are not really meeting up to the quality, if you will, of your reference frame. So like in this case, if you only have one very good reference frame, all the other frames are going to seem not so good by comparison. Normalization is a relative metric. If I didn't use, or he didn't use, this frame as his reference and he chose one of these others, then all of these frames are going to look like they're much better quality. Of course, the quality hasn't changed. It's just the relative distinction from frame to frame that has been adjusted. That's all I wanted to say about that, because I know that that's another separate issue. That's not what's going on here. The problem here is that why wasn't the rejection as good as desired? So I'm going to go ahead and load his files basically into image integration. Here they are. And we need to load the files in the same way that NSG does because these are already normalized. What we would do is we would do no normalization, and we want the weights to be determined by the fits keyword that normalized scale gradient puts into the file, and it has a name. It's NWeight. So we also want to choose a rejection method. What was noted, what the information that I received, that is that this particular gentleman, he chose different methods and he kept getting the same result. So that wasn't very encouraging. Again, compelled me to say, what in the world is going on? So we are going to choose a method, and one method, and I'll get to other methods in a moment, but kind of a standard method is to use the Winsorized sigma clipping. I'm going to use this because there's an implicit understanding of the thresholds that we'll use, which you control in the next tab here. But I do want to say no normalization here. Sorry, you got to set up the rejection method, no normalization, because it's already been normalized. And then, of course, you specify the sigma thresholds. This is the key, as you'll see in a moment. I have logic for determining what sigma threshold you should use, or how this behavior you want to manage when you are adjusting this particular parameter. I'm going to say that my standard is 2.2. There's a very good justification for this, and I have that justification in one of my videos at atomblockstudios.com. So I'd encourage you, if you're not a member, this is the reason why you want to be a member of my website. But this should give us fairly good rejection, and then everything else is fine. All I need to do is to go ahead and produce the integrated result, and what I'd like to see is how good is that rejection based on what I would normally do. That was the first thing that I wanted to figure out. Okay, here are the results. If we look at the rejection map and we zoom in, you can see that it did, in the rejection map, it did basically, those values were detected, and so some fraction of the values that are associated with those satellite trails are being rejected and not included in the average, in the mean, which means they should not appear in the final result. So this was good. I saw that. I'm not going to worry about the low rejection. There's not much there to see. And then we should look at the integrated result. Well, here it is. I will zoom into roughly the same area, and what we'll see is that, well, I don't see very much in the way of satellites. I thought it looked kind of good. Maybe you can see, maybe there's a little bit of a something here, though I've got to say, there are two other comments I've got to say. If you don't have absolutely complete rejection, that is actually normal in the sense that there are going to be values which are so close to the sky value that they just ultimately don't look like outlying values. The statistical rejection that you would like to get mathematically is difficult because those values are indistinguishable with so many other values that are within these pixel stacks. So if you don't get absolutely perfect rejection, that is normal, but I would have expected better rejection than he showed, and it is better rejection than he showed. You'll see here, compared to the version that I just showed here, there is much better rejection based on the normal way that I do things compared to the whatever the method that he did is. And that's actually where I want to go next with this story. So I sent him this result here. I said, look, the rejection actually looks pretty good. What were your settings that you used in image integration? And the response was, and you got to have a drum roll here, the response was, well, he said, I was just using the default settings. And I said, okay, now I understand what's going on. He had changed here the different rejection types, which may or may not be terribly useful to do, but he did not optimize the sigma threshold. And it's the sigma threshold that you need to adjust that actually does the work, if you will, of determining what outlying values are. And the default, and I don't call them default values, the initial values that are in this tool are too conservative. They just don't reject that much. And maybe that is a good place for them to be, but it always is that you're going to want to manage those parameters to get kind of the optimal result. So I have a video on my website that it's called a PixInsight TV video, actually, and it is all about this very idea. This is one of a number of things in PixInsight that I think is very important to recognize, which is that defaults are an illusion. There really are no defaults. It's really this understanding of how a process works that you need to configure the parameter space in such a way that it gives you an optimal result. And this is just a perfect example of that. Now, let me go back to this other idea. If what you see here in the result that I just did still isn't good enough for you, and you want to have yet better rejection in some way, you can force absolute rejection in any particular stack of pixels that you would like, any values in that stack of pixels, by doing a technique that I call selective rejection. All you do is you make pixels black, and you're going to be taking advantage of this parameter here. You can specify a rejection low range, if you will. Everything at that number and below are going to be completely rejected. So if you make zeros and only zeros, and zero values are not something you expect to have in your data, not useful data anyway, right? So you can make zeros in images. If you have not seen other videos on my YouTube channel, I would encourage you to check it out. One of those videos is on what I called easy selective rejection. You can see in that little thumbnail where I have painted in an image, and then when you combine with image integration, all of that goes away. Any of the artifacts in those areas, once you integrate, are going to disappear. So, now that I know that he wasn't using anything, what I'm going to do is kind of a tricky thing here. I'm going to set up the tool as if it were basically the defaults here. Now, presumably he had it set up, correctly, otherwise correctly. So I'm going to set this back to 3, and let's see what we get. So we'll do a quick integration again. It should be fast because it's cached these images in memory. And now let's zoom in here to the rejection map. You can see that there is some rejection here. So let's go ahead and look then at the integrated result. We would still expect to see some rejection. But it's not, there it is. There is some rejection, but it's just not enough, basically. Not all of those values are totally being rejected. And sure enough, we basically get the result that he was showing, where we have some of this little leftover, if you will, values that just don't completely disappear. Now, he wrote in his email, well, maybe I'm just being picky. No, you're not. You're not being picky in this case. This is really more about an understanding of two concepts. One is, of course, that there is no default. You're just running a process with set values. In PixInsight, rarely is that going to be optimal. You really need to always configure the parameter space. And then there's this other idea that at Atom Block Studios, we really do go into the details of what that parameter space looks like, about how to adjust things so that you really do get an optimal result. I wouldn't consider this an optimal result, right? So we can do better than this. And I demonstrated that just with kind of a typical way of setting up the tool. But now I want to do one final step, which is what happens if we set up image integration this time. And this is why I saved this rejection map for my first attempt, which was just with Winsorized Sigma clipping. What if we do now change it to another one of these algorithms? The algorithm that I would like to change it to is the extreme studentized deviate algorithm. It is my favorite one today because it just does things so well. And I can now, with this data set that was given to me, I can kind of show you the difference, which is neat to be able to demonstrate. So we'll go back here to everything is still set. All I'm going to do is change this to the generalized extreme studentized deviate test thing. The important thing about this tool is that it does not work on a sigma threshold. Instead, it works on this idea of kind of a likelihood that a value is going to be one that is an outlying value. So I have on my website, which I can show you here, a section dedicated just to explaining how this is different than the normal, all the other kind of algorithms really, the normal sigma threshold method of determining outliers and knowing how to adjust that parameter space. Here, it's different. This is a completely different algorithm. And one of its benefits, really cool benefits, is that it really, really works hard to only capture those things which are outliers, which is really interesting, but it does so in a strange way. So let me adjust the parameters here. So the outliers, well, I explain in my video, so you really got to become a member and see this. One of the things that determines how either conservative or aggressive it is with the identification of outliers is the significance part of this test that it does. And so I'm going to make this a much larger number to dramatically demonstrate this example. And I need to lower this one as well. So with that, let me go ahead and run this again. Let's be sure that I have everything correct here. No normalization, fits keyword, yes. This is correct. No normalization with those settings. I think everything looks good. Let's run it. Okay, so here we are. And this is the last thing I want to demonstrate. I'm going to show you the high rejection here. And here's the integrated result, which we can compare to the first one. Why don't we do that one first? And so this one here is the ESD result here. This one is the Winsorized result here. And if we compare the two, not that, sorry. Where's my ESD thing? There it is. We compare these two by blinking them. Oh, I gotta click on the one behind. And I have to match them. I'm gonna do a couple of things here. Match. Now we should be able to blink them. It's pretty tough to see the difference, but let's zoom in some. And blink. Yeah, I mean, they both pretty much do the same thing in terms of rejecting those satellite trails, but here's the part that I want to show. This is what's interesting. So you're getting an equally good result, I would say, but look at the rejection itself. So if I do Control A here, and we zoom in, here's the cool thing about the ESD is that it is only rejecting. These two are both screen stretched in a similar manner here. So if we compare them in the same places, you'll see that we're getting the rejection of the satellite trails equally well in ESD, but we are not rejecting anything else that could be useful. So you'll notice here that when we're looking at the Windsorized sigma clipping, because we have that sigma threshold, it's not a likelihood kind of result. We are rejecting many, many other values up to a point. Now, all those little noisy values that are seemingly, that it looks like noise here, those could be low, we don't know for certain, those could be low-level, signal that it's not like we're throwing away information per se, but we're averaging fewer values at the end of the day. And the more values we average, the better basically the signal noise is going to be. So that's why I'm going to claim that here ESD gets rid of all of the artifacts, all of the, transient things from satellite trails to cosmic rays and all of those real big differences, but leaves everything else alone. And that's actually nice. That is a cool kind of benefit. It's a subtle nuance here to ESD. There are some other benefits of ESD as well. But this is one of those, in that it rejects these outlying values very well without needing to go any more than what is necessary. So I wanted to show that off as well. I hope you enjoyed a little bit of this dive into a person's particular question and why it had some small areas of interest. You can see more information like this, of course, on my website. Become a member, and then you'll see much more of what goes into an understanding of all of these tools and kind of getting the best out of them. Also, of course, I do, occasionally make these YouTube videos. I'm never going to I don't get any money from making these YouTube videos. This is really a community type thing for me. But it is something that I would only do if people are actually watching them. If no one is seeing them, what's the point? So please subscribe to this channel so that you can be made aware that there are others, and like the video, comment down below, let me know if this is the kind of information that you enjoy seeing on this YouTube channel. Thank you very much, and until next time, see ya.